Hello, and welcome to this AWS Tech Talk. My name's Ian Perez. I'm with the AWS IoT Business Development Team here in Seattle. And this Tech Talk is extending machine learning to industrial IoT applications at the edge. And with me today, I have my distinct colleagues from ST Microelectronics, Manuel Cantoni and Marcus Meyer. Gentlemen, welcome.
Thank you.
We also have our special guest from Vantage Power joining us later today. So just to level set on what we'll be discussing today, guys, I think we've got a chock full agenda. One of the things that we'll start off with is just a brief level set on IoT and what's happening in the landscape, specifically from an Industry 4.0 perspective. A lot of jargon, a lot of market hype that's been thrown around in terms of Industry 4.0, industrial IoT. So I think we want to dive a little bit deeper in terms of what are the specific industrial applications that we see ripe for disruption through some of the solutions that we're going to talk about today. We've got this fascinating demo rig that Manuel's going to walk us through in terms of how does this relate in terms of real world use cases for industrial IoT applications. So super excited about that. And then we'll shift gears a little bit to Marcus in terms of talking about what is the evolving role of artificial intelligence, be it machine learning, deep learning, and how does that play in terms of industrial IoT applications at the edge, which is very much the theme of today's discussion. And then lastly, we'll flip over to our special guests over at Vantage Power to talk about their specific use case for edge compute and machine learning for industrial applications. So super excited about that. So first off, guys, I'd love to hear a little bit more about your background. Maybe Manuel, start with you in terms of background. How long you've been at ST? Give us the works.
Been in ST more than 17 years now, I live in Portland, Oregon, and I'm part of the American Marketing Organization, and I'm IoT Marketing Manager, supporting the partnership with AWS specifically, and enabling ST solutions in the AWS ecosystem.
Fantastic. Marcus?
Yeah, my name is Marcus Meyer. I'm based in Santa Clara, California. I've been with ST almost 26 years now. Oh. And I'm the product marketing manager for the microcontroller group for the West Coast. And some of the devices we're talking about for computing on the edge are our STM32 microcontrollers, which is what I'm responsible for.
Fantastic. Again, thanks guys for being here today. So Manuel, why don't we start with you, and maybe you can tell us a little bit, what does ST do? Also talk about how does ST view the world of IoT, because IoT can mean a lot of things to different folks. Take it away.
Okay, so ST, first of all, is a global semiconductor manufacturer company. We have various product lines. STM32 is one of them, and we are leading the market in the embedded microcontrollers with more than 4 billion shipped out to date. We have various other components in our portfolio, a broad portfolio of sensors, MEMS sensors and actuators. We have analog components, comparator operation amplifiers. We have connectivity options, for example, BLE devices, and power management and secure components. So basically all the ingredients that you need to build a device, an end device that can somehow connect to the internet. So, and in regards to IoT, we like to call it within ST the IoT a movement rather than a market segment or a specific vertical. It's the tendency of connecting things to the internet and feed the cloud with data to then create value out of that data. And from our standpoint, our goal is to sell our components and to have people build things with our devices. So how do we enable that in the IoT? So the first step is providing examples, developing kit examples like the one that you show here that are formed by various ST devices, and they comes in various shape and forms. They can be form factor, they can be scalable, they can be much more or less capable in terms of extendability. And with those development kits, we also provide pre-integrated firmware examples that address specific verticals and focus for us these smart things, smart home and city, and the smart industry that we are talking about today. Together with those examples, you use them in the ST development ecosystem. So we provide configurator tools for our microcontrollers, prototyping software. As Marcus will show, an artificial intelligence toolbox and development IDEs. But ST can take you up to a certain point. We need company like AWS, we need partners to create really an end-to-end experience for our customers. And that's why you have the cloud over there that you see in this slide. To really create an IoT end-to-end experience, you need the internet and the cloud capability. So we have a partner program within ST where we enable partners like AWS that provided services different from our core business, and in particular here we're talking about the cloud connectivity.
Sure. Yeah, and I think we reciprocate as well in terms of some of the partner programs that we have on the AWS side, which obviously ST is a part of. You hit on a couple of really interesting points. One in terms of how to create value, which I think is absolutely paramount in terms of IoT strategies and solutions. So I know we're going to spend a little bit of time on that later. So maybe we can pivot a little bit and talk about Industry 4.0 specific examples. What are some of the specific use cases that ST has seen? Obviously, you guys have been around for quite some time. Any insights you can share in terms of what are organizations, customers doing with the technology that ST is providing?
Okay. What is Industry 4.0? It's the fourth industrial revolution, where we have the capability of getting together technologies like pervasive sensing and creating data out of machines, both from the operational standpoint and from the actual environmental or actual real world data that comes out of those machines, together with the capability of having this data grouped in the cloud and creating and with the help of machine learning or artificial intelligence create value out of the data themselves to, in the end, get actions out of those value. So obviously we've been around more than 10 years. So we've been in the industrial market for a while, and here the whole approach is slightly different because we're not selling a component that is just part of a machine, but we're really helping a machine to be connected, to generate data and then send those data to the cloud, to then enable the Industry 4.0 value proposition.
So it's really, I mean, it's not that certain sensor capabilities haven't been around. They certainly have been around for a long time, but really what we're talking about is almost a democratization of the technology to make it accessible to pretty much the masses, right? Yeah. Whether you're a huge multinational conglomerate that has manufacturing facilities over the world, or maybe you're just a small niche startup perhaps that has a need for that kind of sensing technology.
Absolutely. And in terms of technology evolution, so we're talking about vibration sensors that now are like 4 millimeter by 4 millimeter, instead of being a machine that an operator can actually needs to go and retrofit. And really that is a mind shift, because it helps us moving from fix it when it's broken, which is what nobody wants to do, to a planned scheduled maintenance, sometimes planned and useless maintenance. So, but it gives you the peace of mind, like when we do all changes in our car. So to condition monitoring, which exists right now with sensors that needs to be operated, to a different, what we call level 4 in this slide, the predictive maintenance. What really the ability of having sensors everywhere, because they're so small and inexpensive also, and not only sensor but also computing in a very small real estate. So it gives you that local computing that enables the full predictive maintenance.
And that's something.
proposal.
Sorry, I think that's something that's key. I mean, it's what we've also been seeing on the consumer side of things, right? With smartphones and other smart devices that have been basically widely adopted, widely available, precisely because the cost of bringing that intelligence to those devices has gone down over the years. So
Absolutely.
very much a contributing factor. So that's a great segue, Manuel, in terms of predictive maintenance being one of the key themes here from an Industry 4.0 perspective. And now, this demo here is calling my attention, as it is, I'm sure, for all the folks tuning in. Tell us a little bit about, what problems is a demonstration like this solving? I mean, what are the proof points here that you're really trying to establish through some of the developer kit that you guys make available? Maybe walk us through the demo.
Okay. First of all, let me walk you through the technology. So when a failure occurs, it can manifest itself much earlier than the actual occurrence, with if you know where to look and what to sense. So usually the first things that you can observe is actually you can listen in the ultrasound range with a specific microphone. You can hear variation of the sound signature of the machine itself. Then there are a small vibration that appears, and you are getting closer to that failure. Then you can observe a power drain that is getting increasing, and as these symptoms appears, you're getting closer and closer to the failure. And then there is actual vibration, noise, actual audible noise, heat, and then in the end the machine blocks. So you want to act as fast as possible. That's why having multiple types of sensors that observe what the machine is doing is really helping. And this varies from machine to machine, of course, but it's really helping identify signatures of an early failures.
I see. Interesting. So yeah. So and if you blow this out over, let's say, a large scale type of operation, it's perhaps many different types of machines, but different sensors deployed for the right kind of machine, and eventually creating, I would say, kind of a meta model of that, right, in terms of all the data that's coming in, which I know you'll get into in a little bit.
Absolutely.
Yeah.
And the idea is that you observe the same machine. You have, let's say, hundreds of machines on a single factory floor. You observe all of them. At some point, you will notice something different in some of them, and maybe you have multiple factories with those machines. So you can identify the signature and then deploy it in all your factories. Really come ahead of the curve and do the maintenance when it's needed, and on those machines that claims for the maintenance, rather than on a rotating schedule try to maintain all of them. So this rig in particular, what you are seeing here is a couple of identical motors that rotate these plexi rotors, and the motors themselves are identical, and the rotors are slightly different. We put a nut and bolt on one of the sides, so that basically when it rotates, it will show some vibration, some off balance vibration.
Yeah.
These are off-the-shelf motors. What do we do with them? We basically retrofit them with a Solidal sensor node, which is this stick that you can see over here. There is a full IoT device. It has a microprocessor on board, so it can process data. It has sensor on board to drive the sensor and then to take in the data, and one mean of connectivity. In this case, the connectivity is IO-Link, is a serial industrial communication bus that will then be ingested by this master board and sent, I'll explain how, over to the cloud. Okay. But the bottom line is these sensor sticks are so, as I was saying, tiny and inexpensive, that really enables that democratization of data. It's not a machine that needs an operator to be operated by itself. It's a stick that you put there and you forget about it, and then data will come in for the life cycle of the device itself. This helps you also to do brownfield installation. You don't want to refurbish your whole factory floor with new expensive machines, but you can start observing what you have.
Got it. And so this is kind of the staging, handling the staging of the sensor data that's coming in. Did we talk about what this board does?
This board is the motor control, so it will help vary the speed of the two engines. And then you will notice some ordering part number. These are all kits that are available from ST, so you can build your own with our help in this.
Very good. And And so, are we going to talk a little bit about what you have here on the
Absolutely,
front? Yep.
absolutely. So this is now an isolated rig. So it's what comes out of this is a serial communication. So what do I do with the data? Here, the data resides here for now. I am connecting via USB to a gateway. That it's our new development kit of STM32MP1. Our newly launched application processor, and this is a Linux machine that runs AWS Greengrass.
I see.
So what it does, it gets the data, the sensor data from the rig, creates two IoT shadows, two things that will then be duplicated in the cloud and start getting data out of and basically ingest data out of the real sensors.
And so those shadows are representing the two
Yes.
motors that you have here, kind of a visual abstraction, or I should say virtual abstraction of those devices. But just to be clear, so Greengrass, this could be effectively an industrial gateway.
Industrial
type of
gateway, an
device.
industrial
Okay,
PC of some kind, absolutely.
yeah. I see. Very good. And then to the right we have...
To the right, we have the IoT Discovery Kit node. Is our to-go kit for cloud development. Is enabled in the AWS device catalog, and it runs Amazon FreeRTOS. And this is to demonstrate that you don't need complex cabling and wiring infrastructure. You can post data directly to the cloud if you want to. And in this case, we are posting to AWS IoT Core, humidity and temperature parameters out of a completely wireless node. This is completely disconnecting and still posting to the same endpoint of data ingestion.
Got it. So in my mind, just to kind of simplify, basically we have a more robust platform that could be running a gateway or hub with significant, perhaps more significant amounts of CPU memory capability, which would run AWS IoT Greengrass, and then you have a board that's more representative of what would actually go in a simple endpoint device, perhaps that's running Amazon FreeRTOS. So MCU-based architecture versus MPU-based architecture. That's kind of the rough breakdown, correct?
For cloud connectivity.
For cloud
Absolutely.
connectivity.
Absolutely.
Great. Fantastic. Very good. And then in terms of, beyond the physical nature or the physical aspect of the demo here, you obviously are doing something with that data.
Absolutely.
How are you actually, once data egresses these boards, tell us a little bit about what's happening downstream.
Okay, so we built a full predictive maintenance platform to show how data ingestion work and what do you need from the service standpoint to ingest and then visualize the data. So we talked about Amazon FreeRTOS, we talked about Greengrass. They all feed in the same endpoint, which is AWS IoT Core, that receives the message with the payload of the actual sensor node. And then there are other services, the storage that is needed, and the functions that manages the Lambda function that manages alerts and notification based on what the data looks like.
So event-based processing taking place on the back end based on the payload, and from there you can start to do more interesting things in terms of what's happening behind the scenes. Okay, fantastic, very cool. So maybe from here, would it be good to? I noticed you have a couple of cool-looking dashboard icons there. Maybe it'd be good to understand how does the data get consumed and presented. Right?
Okay,
if I'm an operator
absolutely.
in this let's say in a industrial type of organization, what am I actually seeing at the end of the day?
Let me fire these things up then. So it's we built a web dashboard with which you log in like you would log into your account on AWS, and we basically declare the nodes that you want to visualize on this dashboard. We have the nodes on the right, the node on the left, and then the wireless node, the humidity and temperature. And what you are seeing here is a continuous data stream, so data that comes out of the sensor. So again, sensor node goes to the Greengrass, goes to the cloud, and I'm visualizing of a web browser. So if I start the rig, and we can get this started really quick.
Oh, wow.
There you go. These are the vibration that starts. Okay. they start kicking in. Give it a couple of minutes, you will start seeing a different signature on these between the two sensors. So they blink green when they connect, and you will see that the data has been updated. And on the FFT, on the frequency domain graph, you will see that specific signatures are starting to appear. So the device on the right, for example, is experiencing a big spike in the lower frequency, which is 3 times higher than in amplitude than the one on the left.
So that could be perhaps an event trigger that then provides some alerting or remediation plan, if you will, right?
Exactly. This is just a dashboarding right now, just showing the data. What I can do then, I can do some asset condition monitoring, put some thresholds to create alerts or alarms. And I'm seeing that one device is in this is normal configuration, the other one is in the almost not okay. It's the amplitude is getting too big for so you might want to take a look at that.
Sure.
These are just thresholds, so this is no intelligence at this point, and it's just depending on data, I go here or I go there. Same things on the temperature. And then there is a third. So if you imagine to have multiple nodes across the country, we also have a dashboard where to visualize geographically where the nodes are. So we generate this demo out of our offices in Sicily, in Italy. So that's why you see the 2 rigs coming out of there.
So that's more of a kind of a fleet management.
Fleet management device, absolutely.
Very cool. And so one of the things that I know we didn't spend a whole lot of time on. Obviously, this is relying on connectivity back to the cloud in terms of getting the packets sent over to IoT Core and then eventually represent them here in the dashboard. But I'm sure you've heard sometimes there's scenarios where a certain manufacturing facility, for instance, might be completely hardened, or it might be that it's just subject to intermittent connectivity for whatever reasons. What does the solution look like in terms of can you have more of the analytical insights basically localized to the environment in those kinds of scenarios?
That's a very good question, and the answer is absolutely yes. So that's why we build the work frame using Greengrass. So the same function that was managing the alerts and was running on the cloud can be run locally on Greengrass itself. And Greengrass will mask the cloud for all the nodes that are behind it. So for the sensor node, it's completely transparent if the cloud is there or not.
Very cool. Yeah, very cool. So really, it's almost allowing that autonomous behavior mode. If you don't have the connectivity, or if it's intermittent connectivity, you can still have local actions being taken place on behalf of the motors or whatever's being monitored.
Absolutely. One other key point of all these sensor nodes, they are not immutable in time. They can be updated. So all of them can, with some means of connectivity, can be fed the new firmware. So they can basically change their behavior over time.
Oh, that's a good point. Yeah.
And these via serial, these Amazon FreeRTOS via over-the-air update that are natively supported in Amazon FreeRTOS itself.
Yeah, and that's key, right? I mean, being able, once you launch a product, or even if it's in a brownfield environment like you mentioned, I mean, you want to be able to continue to iterate and support a healthy innovation curve, and certainly providing over-the-air updates for whether it's firmware or perhaps it's the application logic that you might be running on an industrial gateway. That's absolutely key. Mm-hmm. So very, very, very interesting demo, Manuel. I appreciate that. So maybe one question is, so for viewers that want to get something like this started, they want to do some prototyping. What's kind of the right starting point for them? Is there an easy place
so if you want to do basic prototyping to connect a node to AWS IoT Core, we will definitely recommend the AWS the Discovery IoT node, Discovery Kit IoT node, which is present in the AWS device catalog, and you can download all the firmware from there. The other kits are all available from ST.com or from our distributor. The MP1 Discovery Kit will also be enabled in the AWS catalog as a Greengrass starter kit in the next month. And how to put together the overall kit, we are in the process of working on an application note that and delivering firmware that shows you how to basically put all of this together. And instead of using this demo motor, use your actual machine with the same sensor sticks.
Fantastic. So it'll be a recipe cookbook for that. That's
Correct.
I'll be looking forward to that one. See if I can stitch something together on my own at home. Oh, very good. Very
Let me
good.
turn it off now.
Okay. Thanks, Manuel. Appreciate that. So, Marcus, maybe we shift gears here a little bit. I think now with what we got to see from the demo and kind of the basic dashboard views, I think it'd be interesting to hear from you. How do you see the evolving role of artificial intelligence and a lot of the tools that are basically manifesting? How do you take that and perhaps layer it on to now really add some of the predictive capabilities that most folks might be interested in?
Yeah. So AI has been a big buzzword in the last few years, and mainly right now, artificial intelligence is run on very big machines, mainly in the cloud, and consumes a lot of power. And for example, if you have your sensors in the field, then you have to transmit a lot of raw data, so you need a lot of internet bandwidth, and then there's also security issues. So I don't know if you want to share your data in the cloud. So this has been how it has been done historically. But now what we're doing, or what also the trend is to move some of the AI processing and the machine learning processing to the edge. So what does that mean? So that means that you have a lower power consumption. Also, you basically less critical data, raw data transmitting, so you already basically pre-compute some of the data, and then also certainly the bandwidth is much lower. And then also you need much less processing power in the cloud. So this is basically you're moving some of the processing from the cloud to the edge. And this can be done on microcontrollers or microprocessors. It always depends on the use case.
And that's, one of the key points I think that maybe, Manuel, you were making before. I mean, in terms of when we talk about the edge, there's the concept of gateways and hubs and kind of more industrialized computers that have significant I call it horsepower, memory, CPU, connectivity. But you might also have the actual endpoints themselves. Maybe we call it deep edge, right? And I think that's what you're going to talk about is how can you actually implement AI, ML workload capabilities at the actual endpoint level, in addition to what might be done on a gateway level.
Correct, yeah.
So maybe, before we get too far in terms of what can be applied at the edge versus the cloud, I think, for those of us that maybe don't come from an AI background, maybe just deconstructing the topic for a little bit and telling us about, what are some of the branches of AI, which ones have historically been more adept to run in the cloud versus which ones are now being optimized to run at the edge?
Yeah, so let's first start out with, what is artificial intelligence, or AI, how people talk about. So this is kind of the superset of all the studies where machine basically try to mimic the human brain.
Sure.
Because, we're talking about since, the 50s, the Jetsons and so, that basically there's robots and computers which can basically do the same thing what humans can do, but certainly we're still not there yet. But certainly there's been a lot of study as to artificial intelligence. How can we really kind of mimic the human behavior, the behavior of the human brain? So what is this? So it's interaction with the environment, knowledge representation, perception, and specifically learning is a big portion of that, because that also then goes into the subset I'm going to talk to in a minute. But then also, in order to do that, you need some key ingredients. So one is computer science, statistics, and a lot of mathematics. So now let's talk about, for a second, as we mentioned, there's deep learning, machine learning, there's a lot of buzzwords out there. So artificial intelligence is the big superset, and then machine learning refers to the software research, which enables a wide variety of algorithms to basically, over time, to learn and improve the behavior. And I think the big word here is learning, and I think this is the key word. And then deep learning goes even further it utilizes the learning algorithms and then derives the meaning out of the data and uses multiple layers and specifically neural networks to basically mimic the neural networks of the human brain.
I see. So that provides a pretty good breakdown, I guess, of some of the different branches of AI. From kind of bringing this back to if I'm looking at engineering or developing an IoT solution, making a decision of whether I go with a microprocessor-based enabled device versus a microcontroller-based device. Yeah, again, edge versus deep edge. Is there anything to bear in mind in terms of which is more appropriate from the AI branches?
Well, it really depends. I mean, there's a lot of already models out there, and it really depends of kind of what your use case is. And depending on that, you can decide, for example, computer vision, image recognition, and something like that. That's probably something which uses a lot of computing power, which is more to be done with higher performance machines or in the cloud. But then some things like we're talking about predictive maintenance or human activity recognition or object detection. So those are more things which can be done with machines with lower performance, such as microcontrollers or lower end microprocessors.
There's also a latency piece. So the closer you go to the deep edge, as you mentioned, the faster you are to observe and respond. Exactly. Which is in the predictive maintenance example, that's
super
key.
critical. Yeah. Agreed. So maybe Marcus, you can walk us through again, just thinking of this from an embedded developer, IoT practitioner perspective. What are some of the steps that one needs to take into account? Are already committed to there is a necessity for AI ML perhaps. What are some of the basic fundamental steps that need to come into play?
Yeah. So there are 5 key steps in building a neural network specifically on the edge. And so the first one is really capture a lot of data. And so what you have to do is, so you basically have to basically get a lot of data from your behavior, and that can be data sets out of thousands, 10,000, or even up to 1 million data sets. So that means a lot of that is really happening in the cloud. Sure. So you're doing this, you capture the data, and then the second important step is you have to clean up the data, make sense out of it, label it, and then build from that a neural network topology. So then the third step is then you decide to use a specific neural network model, and there's a lot of out there like TensorFlow, Keras, Caffe, and so on. So you choose a certain model, and then you train this model. And then once you have those steps done, so those are like fundamental steps. So you train, you basically build your model, you use your data, and just for the data set. So depending on your use case, you have to collect the data by yourself, but there's also certain use cases where there's models out there which you can, some of them are open source, some of them you need to buy. So when you have all this done, then you have a trained model. So then you can see how do I transfer this into onto the edge. And this is where we come in with our new tool, the STM32Cube.ai, which takes this trained model and then basically converts it into code which can run on microcontrollers. So this is the step number 4, and then certainly once you've done that, then you can either do it on your computer or run it on real hardware. Basically process and analyze the new data using the trained neural network, and then also, as we've mentioned before, you have the upgrade capability. So then if you have enough new data, basically, and then move that to the cloud and train the new model, basically, you could basically then push back this new model and reprogram the device on the edge to basically improve the behavior of your device.
Which is that virtuous cycle that we I think we alluded to before, where you could again start with the development of that model as you suggested in the cloud, perhaps using services like Amazon SageMaker, refining that model, pushing it out, optimizing it, which is really the value that you guys are providing, optimizing that model to run on microcontroller devices. I guess if it was running on a microprocessor device, then we could use things like Greengrass, obviously with SageMaker Neo integration to do that. But it is that cycle, right? With constant refinement and being able to basically improve models over time. So that's fascinating. Now, in terms of, I know you mentioned a couple of the frameworks that are out there. Is there any specific framework that comes to mind when you start thinking of, okay, if I'm going to run this on an MCU-enabled device, should I go with one framework versus another, or is it fair game?
So that's a good question, because there is a lot of frameworks out there, but as we mentioned before, historically they've run on computers or in the cloud. So some of them are TensorFlow, Keras, Caffe, Lasagne, and so on. So certainly we can all use them all as inputs with our tool, and then we can run some algorithms on them to optimize them to basically get them into a size where they work on the microcontroller. But then also just recently in March, TensorFlow announced a new model, which is TensorFlow Lite for microcontrollers, which is specifically targeted for applications directly at the edge to run onto microcontrollers. And that this was just introduced and will be available also for support pretty soon with our STM32Cube.ai.
So that these kind of optimizations that are happening at the framework level just help that much more in terms of what you're optimizing already today, perhaps.
So correct, yeah.
So I know we talked a little bit around some of the availability of the STM32 on the AWS partner device catalog, but where does one start specifically from what you're showing here? I mean, is there a natural starting point from a developer perspective?
Yeah, so there's a couple of them. So one is certainly the software aspect. As I mentioned, you can download from the ST website the STM32Cube.ai, and which allows you to convert the code, and we also have tutorials and videos on there. But then also we have hardware support, and we have different boards which are supported, and one of them which is supported is the IoT Node, which is also the one we're showing here, and which is available at the AWS developer catalog. And so we have a full set of what we call the Xcube library, which has some examples for machine learning and AI, and so you can use that as a good starting point.
Very good, very cool. And just in terms of the Amazon free RTOS piece, I guess it's maybe worth just distinguishing that. So again, Amazon free RTOS running on the board with the additional libraries that you're providing, basically running on top of that.
Yeah, correct. Okay. And the Amazon free RTOS gives you one capability to basically upload your firmware in the microcontroller from the cloud, which allows you, if you created a new model or you retrained your model, you can download that and upgrade that without somebody needing to go out there and do any changes.
Very cool. Yeah, those OTA updates are absolutely key. Marcus, maybe any other options? I mean, if we kind of look at the ST portfolio from a big picture perspective, again with AI in scope, what other options are we looking at?
Yeah, so the STM32 microcontroller family has been around since almost 12 years. So we shipped over 4 billion microcontrollers to date, and we have over 40,000 customers using it, and we have right now 900, and we are approaching the 1,000 different part numbers. So currently our tool, the STM32Cube.ai, supports floating point units, devices which are supporting floating point, so that right now all our devices which are using ARM Cortex-M based cores, which are the M4, M33 and the M7 core, they're all supported by the Cube.ai, but we're also working on a version with fixed point, which then will basically support our complete product portfolio of all our devices. But then also one important point is, as we already mentioned, and you see it on this slide all the way to the right, is our STM32 MP1, which is the board here, which is a microprocessor-based application processor using Cortex A7 cores, and it also has a Cortex M4 core as well on the device. And this is certainly also a device which supports, if you need more performance, more complex neural networks.
Fantastic. So yeah, 12 years in the making for the STM32. Obviously, innovation continues with this guy over here. I got to ask, like, what in terms of prognostications and predictions, like where do you guys see kind of the industry going in terms of NPU, MCU capabilities from an IoT perspective?
Yeah, so certainly, as I mentioned, we're working on bringing AI to those families, and we're are continuously improving our our tools and certainly our families to address this market better in the future.
Excellent, guys. This is all really fascinating stuff, really good insights shared. I guess maybe now would be a good time to take a few questions from our audience and see if we can provide some additional insights, some answers to those questions. So let me go ahead and bring up a question and answer here. Let's see. Okay, maybe let's see. We'll take the first question here, which is besides the STM32, which is the microcontroller unit, what other offerings should be considered or could be considered to run ML workloads at the edge, be it on industrial gateways or similar devices?
Yeah, so as we mentioned before, so certainly all the different families of the STM32 MCU series, but then also certainly the new STM32 MP1 application processor with an MPU is certainly a good target if you need more performance.
And in terms of maybe just I'll add a follow-on question there, which is, how does, whether you're starting with an MPU-based device or an MCU, how does one transition from, let's say I'm a developer, I do some rapid prototyping, how do you transition from that developer prototyping mode to an actual production type of
So when you get our developers kit, you get all the schematics, all the layouts, and all the code available and readable, and basically you develop on the development kit. Then you take the code and start trimming down all from the actual schematic all the parts that you don't use. The code is immutable, but the boards will basically adapt to what you're actually needing to do.
And therefore shrinking, you could
shrinking, going form factor, etc.
Interesting.
And for this prototyping, that's why we put also expansion boards or expansion capability on the boards. We have Arduino connectors, PMOD connectors, so you can take this as a starting point, add what you need, create a mock-up of your thing, and then go form factor, always keeping the same code. So you do all development and then shrink down.
Excellent. Very good. Looks like we got another question here, which is, what is the relationship between ST and AWS IoT, or I guess ST Hardware Solutions and AWS IoT?
So as I was mentioning in the beginning of the presentation, the two core businesses are very complementary. So we are in the deep end, the deep edge, as we were mentioning, as the solutions that generates those the data that AWS can ingest and manipulate. So and that's why we are in each other's partner program, and we jointly approach common customers that when they need end-to-end, they will need both components to build the solution.
Very good. And I think we spoke. We made a couple references to the partner device catalog, which actually shows the final outcome, if you will, of some of the relationship building or relationship activity that we have. Next question here is, where can I find the STM32 MP1, and will it ship with Greengrass?
So right now the MP1 you can find on the ST website, and certainly you can buy it for our partner distributors. And in terms of Greengrass, this is something we're working on right now, and I think as it will be available in the coming months, and I think as soon as it will be available, it will be in the AWS developers device catalog.
Great. Excellent. One other question here, which is, what is the role that Amazon FreeRTOS plays in AI ML solutions running on the STM32?
So Amazon FreeRTOS takes the complexity to connect a thing to the internet out of developers' end. So a very solid framework a very solid solutions to connect securely and to provide applicability. So what are you using out of this feature in an ML scenario is the applicability of the firmware itself. So, but the ML, the output of the cube, the STM32 cube.ai will be a library that runs alongside on Amazon FreeRTOS, and that can change its behavior through OTA.
Very good. So yeah, so going back to the secure connectivity and the ability to do over-the-air updates for firmware is basically where Amazon FreeRTOS is delivering the value, and then you have the additional richness in terms of libraries for AI/ML that you guys are providing. I guess one last question here before we wrap up, which is I'm new to the world of IoT or industrial IoT specifically, it seems. How do I get started with AWS and ST solutions? I think we already mentioned the partner device catalog a number of times. Maybe it's
a good starting point. And I will, if you need to pick one of the kit to start dip your feet in the water, I will definitely recommend the device, the Discovery Kit IoT node, this device over here. And we'll provide links on the video, and it's on the presentation as well. It's the perfect kit. It runs Amazon FreeRTOS. It has already sensors on it, so you have it's a single board computing that will allow you to build a plethora of IoT applications.
With the option, again, like you said, with expansion boards,
yes.
Whatever makes sense.
There are a lot of connectivity options on the board, and if you don't, so there is Wi-Fi, there is sub-gigahertz BLE, but for example, there's no LTE connectivity. We have an add-on board to provide the LTE modem.
And as I mentioned before, it's also a very good board to get started with AI or machine learning. Absolutely. Because we have already full function packs available, which basically gives you a good introduction into AI on the STM32 specifically with this board.
Yeah, and that's a good point. I mean, in terms of, I know you mentioned some of the open source models that are out there. I guess this is where I would add, if you have a look at Amazon SageMaker, we have a number of models there that are basically ready to customize and deploy, and certainly can be leveraged with the STM32 or with Greengrass for that matter. So that's all for questions. I want to thank Marcus and Manuel for coming out today. Excellent insights shared. Great demonstration. A sincere thanks to both of you. I look forward to the next chat with you guys.
Okay, thanks for having us.
And now we'll turn it over to our special guests at Vantage Power to hear about their specific use case of using machine learning for industrial IoT applications at the edge.
Hey, thank you for the introduction, Ian. I'm Stephen Gallagher. I'm a senior systems engineer at Vantage Power, and we're very happy to be here today to talk about some cool problems we've been working on with Amazon. I've been here for about 2.5 years, and I worked across control systems development here, and I've got more involved in our cloud infrastructure and data analysis capabilities, which has led me into this project that we're going to talk about today. But to get started, here's a bit of background about the company and what we do. So we're a small startup. We're based in London in the UK, and we aim to improve heavy-duty vehicles, really. We're planning to reduce the emissions of heavy-duty vehicles through a number of different technologies. We started off developing hybrid retrofit solutions for London's double-decker buses. This led us into OEM solutions for a brand new bus, which you can see here on the right. It was London's first triple-axle hybrid vehicle, so we're pretty proud of that. We also develop our own battery packs, lithium-ion based for these vehicles. They're also applicable to electric vehicles, so there's some space that we're also getting into. We do the control systems for these vehicles, and we've also added a telemetry system onto these vehicles, which connects them to the Amazon cloud and streams a lot of different bits and pieces of data from the powertrain, which is something that's pretty revolutionary for the bus industry to have connections to the cloud and GPS and data streaming back and forth. So it's quite new for the bus industry. We're one of the first to be doing it, and we're really excited to dig into that data and look at some cool different projects that we can do with it. So today we'll look at 2 of those projects, 2 that we have been working on with Amazon. One is a predictive maintenance model for lithium-ion battery packs. Battery packs are made up of thousands of individual cells. These cells are as small as the types of cells you would put in your TV remote, but scaled into the thousands, you can make a very powerful battery pack that can power something like a bus. And we have tens of thousands of these things in our battery pack, which you can see a rough model here above of how this battery pack goes together. Cells are inherently quite fragile. They can fail at any point, and these failures are bad overall for the battery and for the vehicle. If it's a slow failure, then it tends to drag the rest of the battery pack down with it. If it's a catastrophic failure, it can lead to an unsafe incident on the vehicle. But what we want to do then is to identify the cells that will fail. And to do this in advance, we want to know about it before it's going to happen. This will have a big impact for our customers. We can contact them, we can schedule a convenient service time for the vehicle, and we can go look at it and fix this issue before it becomes a big problem. The other problem then is detecting hydraulic pressure spikes in a belt drive system. This one's a little more complicated. It's a very linked together system. There's a belt driving a hydraulic pump, which drives an air compressor, which the air compressor drives a lot of different systems within the vehicle. The problem around that was within the hydraulic drive system, there's a particular valve, pressure release valve, that should stop the system getting into high pressure states that are damaging. Over time, the system wears and the pressure relief drops to the normal operating pressure of the overall system. This causes spikes to happen. This causes the pressure to rapidly drop, rapidly rise again. This causes impulses on the belt drive system, and eventually the belt breaks. And this is very bad because there's lots of other systems driven off of that belt, and the bus stops in the middle of the road. This is very bad for our customers. Downtime is their biggest woe. They don't want that to happen at all. So we developed another model around this, something that would give us not an early warning system that the spikes are going to happen, but a detection system, something that could spot the spikes as they're happening, which is something we could never do before. It takes thousands of these spikes before the system's going to fail. So we want to know when they start happening so that we can get in and stop them happening before it becomes a catastrophic failure. And the way we do this is through that telemetry system that I mentioned earlier. We have a system in the vehicle that is streaming 6,000 data points a second from different systems within the vehicle. They are coming up in two different forms. There's live streaming data, which feeds this map you can see on the right here. So through our web platform, operators can see where their bus is at any moment in time. And we also get a lot more data in batch form, which is batched on the vehicle into 30-minute log files, and they're uploaded to the cloud into an S3, which we then can use for more detailed investigations. So we created models for these two problems that could clean the relevant parts of the data and also be applicable in the cloud and at the edge, so that we have options over how we run these. And the main goal of the model is to detect and to notify us. We want the notification up front so that we offer our customer better service. And the cloud really offered us the environment to trial these, to iterate them using also the historical data that we've been collecting for a long time. And also then to test at the edge. We were able to use Greengrass to push this to the edge and see how it would work. And the cloud offers the environment to do this less invasively for the customer. We don't need to ask them, can we come visit the vehicle, to add in new sensors or new tools to measure these things. It's all there already, and our engineers can prototype and play around with it and see what the results are without the customer even knowing we're developing cool new things. So for a bit more detail on each of the use cases, we'll look first at the air compressor, which is a little bit more applicable at the edge. This one, we're accessing our batch log files. So the batch log files coming up every 30 minutes, 6,000 data points a second, going into an S3. And we attach Athena to this so that we can query into those log files and pull out relevant channels. We don't need all 6,000 channels at once. We're only interested in a few of them for the air compressor system. And we then connect SageMaker notebooks so that we can query this data out for relevant time periods where we know there has been this spiking problem, so that we can use that in training our model. And with the model that we developed in SageMaker, we compiled this into a Lambda function. That Lambda function would work in the cloud, but also using Greengrass, we pushed this Lambda function to the edge, so it could connect directly to the data that was being streamed rather than the batch log data. So using the data stream, it was able to, with a second resolution, analyze that system on the same pressure sensor and tell us and alert us if there was a spiking event in progress. And the device we were able to use then for this Greengrass implementation was a Oasis 4X box. This is a small Linux computer, similar to a Raspberry Pi really, but the benefit for us is it's ruggedized already. It's suitable for vehicle deployment, and it has CAN networks implemented on it. So CAN networks are very important in the vehicle world. It's where we get all of the information off the vehicle. It connects into all the other networks with different systems, with the engine, with the battery, with the vehicle controller itself and the driver interfaces. So we pull lots of information off of that directly into this Oasis box, and we can run analysis on the vehicle, or we can put that back up to the cloud. And this particular model we developed, it was quite successful in identifying these anomalies that were happening. So we used a sliding window that would move across as the data was coming in, and it would look at the max, the min, and the standard deviation, so that it was learning what was normal. And we, using SageMaker in the cloud, we came up with a training value of what was normal within all of these. So it compared it to what we decided was normal, and it identifies any window that has had a larger pressure drop than is expected. And we tended to adapt this model to have a bias towards the false positive, because we want to know about every event, and if it throws in a few more that weren't true events, then that's fine by us. We'll investigate and discount it and look to improve the model to not flag them in future, but as long as it's flagging all the important ones. And it does this on the vehicle. So we are identifying these spikes as they happen and getting notifications to say spiking events are ongoing. And we can then speak to the bus operator, and we can say it's going to be fine for another week or two, but we should probably schedule it in for a service and come have a look at it before there is a failure. And this massively improves the service to them. They know they can continue to operate the vehicle for that day while it's out carrying customers around London. But also they know that we can come and see it next morning or that weekend to fix this issue and make sure it's not ongoing. And the battery use case, that again was looking at our batch log files. They're coming up into S3 again, and extracted these into IoT analytics. So this was a new use case for us. We were able to use IoT analytics and make this process a little more streamlined, really. It's the same process, essentially. You're extracting data into the data store, and we split that into training data sets, which we used in SageMaker Notebook. The big advantage here, though, was once we had developed that model, we could package it all up into a Docker container and use Amazon ECS to run that. Within IoT analytics as well, we were able to create a container data set. This triggered every day. We established that a day was a good window for this battery use case, because degradation of battery cells happens over quite a long period. So analyzing a day at a time gives us good resolution into how the cell is changing. So the container data set is triggered once a day, spins up this container, which we made out of our SageMaker Notebook, runs the analysis, and any cells that are looking like they've degraded more than another cell is outputted as a result. And again, we set up email notifications on this. So our engineers are getting notifications to say when a cell is looking unhealthy or like it's deviating from the rest of the cells in the pack. And this works by the fact that we have so many cells in this pack. It's pulling in this data from every cell and pulling out the relevant areas. So the data isn't always good for analyzing whether there is a problem or not. When the battery is in charging, it's not a good time. When a temperature has gone beyond the limits, then it's also not a good time. When the state of charge is too high a level, then there's not enough resolution in the voltage measurement for us to run this algorithm. using resources in the cloud, though, we were able to work out all of these regions that weren't useful over a really long period of time, over months worth of data, and establishing what our criteria was for good data. We then extracted all of this good data into a kind of time spliced section of interesting and useful data, and we compare them to each other. So we might get most of the cells, 99% of the cells are operating well together, and then we get one cell that's looking a bit different to the others. We don't need an absolute value of that difference from every other cell. We just need to spot the outlier within all the cells. So as long as we see a cell that's behaving slightly differently to the rest, we can flag this as an anomaly that we need to get in and investigate. And the benefits with IoT, they were huge. It meant the data we were already collecting as part of our solution was immediately available to us for analysis. We were able to use SageMaker Notebook to access vast quantities of data, more than we were ever able to look at before, either on the vehicle or in the cloud, and use that to test our hypotheses, really. We had lots of different ideas about when these algorithms may or may not work. And with the cloud, we were able to test those theories, validate them against some other results that we had, and decide what was good or bad. And with the Greengrass Lambda functions, we were able to test that whole process through SageMaker Notebook, push it into a Lambda function, test that in the cloud on new data. And once we were happy with it, it was simple to push that over to the vehicle and run it at the edge, which has big benefits for us with buses. They tend to get into areas where we lose cellular connection, and parked in bus garages, they lose connection when they're under the roof. So being able to continue this analysis at the edge without cellular connection and queue up the notifications so that we still get every notification. We don't miss it because the data went offline for a bit. And it's a massive benefit to us and to our customers. It gives us warnings then that issues are happening, but they aren't full-on faults. They haven't stopped the vehicle on the road yet. And it means we can provide a service to our customers where we're calling them up to tell them the bus is looking a bit unhealthy, but actually it's still okay, and we'll come out and fix it before it becomes a big issue. This is really valuable to them. They hate to get that call that says the vehicle is stopped in the middle of the road and you need to come pick it up. They much prefer a call that says it's still okay, but we'll fix it. And it makes our product more reliable. It means that we understand more about what's happening in our system. And in future designs, we can account for that. We can make it better because we've seen things happening in the data already. And it makes our cost of support much lower. We're not having to be reactive. We don't have to go out and see these vehicles stuck in the middle of the road and work in unsafe circumstances. We can schedule a good time for our engineers. We can send them out during the day rather than at all hours of the night. And they can do this work in a bus garage, in safe environment, with the right tools and the right people around them to solve this quickly. We're solving issues much faster than we ever did before. And there's massive future potential for this. So the battery case, we haven't managed to get to the edge yet because we're looking at a day's worth of resolution, but we think we can squeeze that resolution down further so that we can spot cells going bad at the edge with much smaller quantities of data. And this would be valuable to us because there can be catastrophic failures of cells. They're not always long, drawn-out failures that are happening over a long time. It also means we can use this learning that we've had in the cloud and these methods we've developed to apply them to other problems. There are a number of different problems going on in the buses that we can use data to solve, and we can help to improve the service that we give to our customers. And this helps us then also to decrease the cost. We're constantly reducing the cost for us to service these things, to have a service team that's smaller and more streamlined. They're targeting better improvements on the bus, and they can even schedule a lot of improvements together because we have seen them all happening, and we know we can lump together. You can fix these 3 issues together on that one day and a couple more the next day because the bus will still last a bit longer when an issue we know is not so serious. If you want to learn more about this, this is a white paper that has been posted on Amazon. It's in conjunction with our partners Luxoft. They've helped us to develop some parts of the architecture here. So you can read more about it there. You can also find information on our website, which you'll find in that link. Thank you.
Special thanks to Vantage Power for their presentation today, and thanks to our viewers for tuning in. This concludes our broadcast for today. We look forward to you joining our next AWS IoT Tech Talk.